Transparent Physics welcomes you to another episode in our NoobsterClass Series on adding two-dimensional vectors. Here we bring it all together. Lesson 5A, what's up with that? We're going to introduce the vector analysis table. Our goals for this lesson are pretty straightforward. We're going to show how we can add vectors together using perpendicular vector math that we learned in earlier lessons, even though we're not starting with perpendicular vectors. And the main idea for this exact lesson is to give you sort of a visual scaffold so that you can visualize what's going on with vector addition, and then we'll build the math upon that. But if you don't really understand what you're doing, you're just pushing buttons. So let's get a picture in your brain so you see what the vector analysis table does, and then we can move forward with actually showing the math in action. Okay, so we're going to take the skills that we learned up to this point, and we are going to start with two non-perpendicular vectors, and we're going to be able to add them to find the resultant using all the techniques that we've learned using perpendicular vectors. So you might be thinking to yourself, well, how are we going to do that, transparent physics? If we're not starting with perpendicular vectors, how do we add perpendicular vectors together? Well, let us see. So we're going to start with two vectors that are not perpendicular, so we'll just draw them out here. The actual numbers aren't super important right now. I'm just going to show you a graphical representation of what I mean here. So we're going to start with vector A, and it's some length pointing at some angle. And then we're going to have vector B, again some different length pointing at some different angle. And we are interested in the resultant. We want to know start where we start, end where we end, and we want to solve for this value right here. We're going to call it R. Now up to this point, because A and B are not perpendicular to each other, we have not been able to solve for the resultant in this sort of circumstance. But what I'm arguing is that we have all the tools we need right now in order to find the resultant. We just need to turn A and B into perpendicular vectors. And the power has been inside of you the entire time. So let's take a look at this. So I'm going to break A into its X and Y components. So A has an X component. Call that AX. And A has a Y component. AY. So AX plus AY gives us A. And we've shown how to break A into its horizontal and vertical components. Let's do the same for B. We want the X component for B. We'll call that BX. And we want the Y component for B. BY. And again, nothing we haven't done before. We've broken B vectors into their X and Y components as well. Now, the trick here is to recognize that it doesn't matter the order that you add the vectors together in. I can travel AX to AY to BX to BY, and that will take me from my starting point to my ending point. So I can go over and up and over and up, and that will get me where I want to go. But we don't have to add vectors together in any particular order. You'll get the same answer no matter what. So I'm going to rearrange these guys a little bit, and when I do that, we're going to get a little bit of extra stuff on the screen, but such is life. So AY, I'm going to pick AY up, and I'm going to move him over. And I'm going to take BX, and I'm going to move him down. And looky, what do we have now? We have a set of perpendicular vectors. We have AX to BX, and we have AY to BY. So we have taken two non-perpendicular vectors, broken them into their X and Y components, and then when we have them in their X and Y components, we are able to now create a new set of vectors. So we have a vector that represents the horizontal line here. We can call this Rx. And we have a vector that represents the vertical line. We can call that Ry. So we are able to now look at this entire length together. So we had a vector A, which had a horizontal component. We had a vector B, which had a horizontal component. We add those together to one larger horizontal component that represents all the individual components. And we have AY, which has a vertical component, and we have BY, which has a vertical component, and we add those together to get our sum. So in the end, we are able to solve for the length of the resultant and the angle of the resultant, because this set of rearranged vectors is at 90 degrees to each other. So we can solve for the angle, and we can solve for the length. And I'll show you how we can do that in a super nice organized way using what we will fondly refer to as a vector analysis table. Well, I don't know about you, but seeing all that vector math worked out makes me parched. And again, always a good time to pause the video, brew yourself a cup of tea. We got a little bit more to go still, so plenty of time to enjoy a little bit of tea before this lesson's out. And congratulations, we can add any vectors we want to now using this technique where we start off with any number of vectors. In this example, it was 2, but we can go infinitely large number, and they are not 90 degrees with respect to each other. We want to take A plus B and get the resultant vector R. In order to do that, we break vectors A and B into their X and Y components, and then we rearrange those X and Y components, and we create a new set of vectors that creates that right triangle that we're used to. So AX plus BX is RX, and AY plus BY is RY, and we can solve for the resultant vector. Now, this technique is awesome, but there are a lot of things to keep organized, and the tool that I'm about to introduce is going to help you make that happen. So I proudly introduce the V.A.T, also known as the Vector Analysis Table. It's an organizational tool that helps us keep the X and Y components where they're supposed to be and lines up a solution that works every time. And there's lots of different ways that vectors show up in physics. Regardless of how they do, this tool is going to be able to help you out, and it turns your undesired non-perpendicular vectors into 2 perfect new vectors, one in the X, one in the Y, and then we can wrap up the analysis with those. The first step in using the vector analysis table is loading your old vectors into it. Those go in the leftmost column. You put the magnitude and the angle of each of the vectors into that column. You want to be careful that magnitudes do not have negative signs. Sometimes when we write vectors, say for instance if we have it sitting on the x-axis pointing to the left, we might write it as a negative 13 meters. That negative never goes into this part of the vector analysis table. We write the magnitude, which is only the length. Magnitude cannot have a negative amount because magnitude tells you how much there is. It's either there or it's not. If it's pointing in a negative direction, that's going to be indicated through the angle. Now, the angle could be positive, could be negative. That's fine either way. But never have a negative sign for the value in front of the comma. And the value after the comma has to be written with respect to the standard angles. If we put it with respect to standard angles, then the trigonometry is going to tell us where the negative signs should show up, and it's going to make our lives a lot easier. Once you've loaded the vectors into your V.A.T, the next thing you're going to do is break the vectors up into their X and Y components. And we already talked about this process in lesson 4. You use the two equations Vx equals V cosine theta and Vy equals V sine theta. Watch out for negative signs that you get as a result of these calculations. Here, it is perfectly acceptable to have negative signs if the vectors are either pointing to the left or down. Once we've broken our individual vectors into their x and y components, we're going to combine all the x's together, and then we're going to combine all the y's together. And we're going to get a new value we call Rx for the sum of all the x components, and we're going to get a new value called Ry for the sum of all the y components. The double line right above where I have the Rx and Ry values written, I like to think of as an equal sign. So the argument is that we have whatever is above it, so Ax plus Bx equals Rx, and Ay plus By equals Ry. So I like to keep that double line in there just as a reminder of the difference in what the vector analysis table means for the values above that double line and the values below that double line. And from that point, we've turned our individual components into a new right triangle. We have a Rx value and an Ry value that are perpendicular to each other. So we can use the skills that we talked about in lesson 3, where we took two perpendicular components and built them up into the resultant again. And we can solve for the length of R and the angle of R. And that's the goal. Now we have the resultant. I'm going to wrap up this lesson with a tip of the hat to Mr. Myers. Mr. Myers was my high school physics teacher, and as a senior he taught me how to add vectors together using this technique. And then I went on to use it for the next 4 years as an undergraduate in physics, because vectors show up all over the place. When dealing with vectors, the vector analysis table is a very powerful tool. It helps keep you organized, it gives you a template for your solutions, there are a variety of different problems that you can address using it, and there are a variety of different topics that you can deal with too, because vectors are all over the place. So you can deal with displacements, you can deal with forces, you can deal with electric fields, you can do this all over the place in your physics career. So next lesson, we're going to show you an example of it in action with a real problem, and you'll see how all the pieces fit together. And I hope you walk away from it realizing that it will be a very powerful tool to add to your kit moving forward. I don't make many predictions, but I am mildly confident that if you move forward in physics, you're going to find the vector analysis table to be very useful. So maybe not now, it might be a couple months or a couple years down the line, you're going to look back and you're going to say, you know what, that vector analysis table is really awesome. Feel free to come back at that time and like this video. If you have any questions about what I talked about in the video, feel free to leave a comment. And to find out what's coming next from Transparent Physics, please subscribe to the channel. Well, this Noobster class on two-dimensional vector addition has been quite the ride. We've covered a lot of content. It's not quite done yet, but I appreciate you sticking around and learning from me how to add these vectors together. And I hope I've made things a little clearer for you on this lesson of Transparent Physics.